Okay.
So let's have a look at 3D.1. We're talking about inflection and shape. So all of this is new to us. We haven't heard any of this before, but it is just a short extension on what we've been talking about. We're using calculus techniques to identify shape. So let's have a look at the diagram I've presented here. And we're learning some new words today. Yesterday we learned about a point of inflection, and we were just looking at the sign diagram of the first derivative to identify. Here we're going to learn what it means. Okay? So a point of inflection occurs when the graph changes shape. Alright, it changes shape. So if we have a look at my diagram here, or at all four of these, notice how over this interval from A to B to C, it's concave up, it's opening upwards. And here is the point where it transitions into being concave down. So that point where it changes shape from concave up to concave down is what we call a point of inflection. Now, there are a couple of tests to determine where it occurs, but generally it's when the second derivative equals 0. So let's look here. We've got the function. When the first derivative is 0, that's a stationary point, right? When the second derivative is 0, that's a point of inflection, provided the sign diagram changes sign. That's going to pop up in a moment. So, concave up, opening upwards. I've got the other language that people tend to use there. Convex is opening upwards. Concave up, convex. Or concave down, we just refer to that as concave. I just use concave up, opens up, concave down, opens down, simple, all right? You're just putting up or down on the column. That's describing the shape. So, they're points of inflection, right? Now we have two types of points of inflection. We have what we learned about yesterday, stationary points of inflection, and we have non-stationary points of inflection. All right? As its name suggests, a stationary point of inflection is when the slope is horizontal. So you can see here, concave up, and we get to this point of inflection where it's stationary. The slope is 0, and then it transitions into being concave down. You can see its shape here is concave down, its shape here is concave up. Same thing here, concave down to concave up. That's called a stationary point of inflection because it goes horizontal at that point. That has special properties we're going to investigate. And then over here, we have concave up. This point of inflection is somewhere in here. It's not horizontal, which means it's non-stationary. Okay, so stationary point of inflection, non-stationary because it's not horizontal where it changes shape. So, so that's the first thing about point of inflection. Now we've said, well, it's going to pop up when we get to the sign diagrams. Okay, so let's get into the example here. This is question 1. And we're presented with this graph, and we're asked to make comments about these particular locations. Is it positive, is it negative, or is it 0? So let's just go through the first column because that's really easy. F of x is the y value. And so we're looking at point A and we're saying, is the y value positive, 0, or negative? Right here, the y value is positive. At point B, the y value is negative. Positive at point C, positive at point D, and 0 at point E. All right? We're saying the y value, positive, negative, positive, positive, and then 0. Okay, f dash of x. What is f dash of x? F dash of x is the slope. So we're asking you, is the slope positive, negative, or 0? So if you look at this point, if you're at that point, you're walking downhill, right? So at point A, the slope is negative. All right, remember if you're walking downhill, that's a negative slope. At point B, it's stationary. It's not going up, it's not going down, it's a local min. The slope at that point, it's not increasing, not decreasing, it's 0. Okay? At point C, you would be walking uphill. We have positive slope. At point D, again, we have 0 slope. Not increasing, not decreasing, it's horizontal. And at point E, we have negative slope going down. Okay, so then we get to the second derivative. All right? So what you need to know about the second derivative is point of inflection occurs when the second derivative is 0. Okay, so if we're looking at this graph, we're going to say, right, the point of inflection is here. That's where it changes shape. That's the point of inflection. It goes from concave up to concave down. So that is where the second derivative is 0. So we can go to point C and we can say, well, the second derivative is going to be 0 there. All right. Now remember, if we have positive slope, the function's increasing. If we have negative slope, the function's decreasing. If the second derivative is positive, concave up. If the second derivative is negative, concave down. Easy to remember. So we can look here and we can see this is concave up. That means at all of these points up to C, from say point A, point B, because the shape is concave up, the second derivative is going to be positive for those points. So we're putting in here, it's positive here and it's positive here. For points D and E, it's concave down. So because it's concave down over that interval, the second derivative is going to be negative. All right, so that's how we're filling in that table. Okay, let's move on to question 2. So we're going to do question 1 and 2 together, and then just question 1 from the examples. So question 2 says, the graph of the function is shown alongside, find f dash of x and f dash dash of x. So we'll do both straight away. We'll have f dash of x will be 3x squared plus 6x take 5. And f dash dash of x will be 6x plus 6. Okay. Draw the sign diagram of f dash dash of x. Alright, so they're not asking about f dash, the first one, they're asking about the second derivative. So if we want to draw the sign diagram of this, we want to know the root. The root occurs when it equals 0. So it's at x is minus 1. It's the equation of a line, and the line has positive slope. So I know it's going from below to above. And you can use your calculator to help you out, right? I showed you the option for the first derivative. There's also the option for the second derivative in graph mode. Or if you graph it, it's the equation of a line. You can see it crosses the x-axis at minus 1. It goes from below to above. So that's how we're getting that. Now this matches with what we expect, right? This is the sign diagram of the second derivative. Remember, I said it's going to be concave down if the second derivative is negative. Okay, the second derivative is negative, concave down. All right, we can see that from the graph. Okay, if this, I haven't drawn it very well. I might just fix it so I can point it out. I'm just going to move the y-axis. It's more here, isn't it? All right, there we go. So we can see concave down, and then here it's changing. X is minus 1 to concave up. All right, you can see that on your textbook there. Second derivative is positive, which means concave up over that interval. All right, so let's answer these questions. Draw the sign diagram done. Find the coordinates of the inflection point. So for an inflection point to occur, there's two things that need to take place. The first is that the second derivative equals 0 at that point. Yes, that's the case. But the second caveat that people miss, because it's almost always true, the second caveat that people miss is these must change sign. All right, so for instance, if they're both positive, then it's not going to be a point of inflection. So that's like a special case that occurs, saying like 2% of the time. You need to watch out for that. It's very unlikely. Most of the time, you do have a change. And regardless, we can look at this graph and observe there's a point of inflection. I can see it. It's changing shape. It's gone from concave down to concave up. So that supports it. So we know there's a point of inflection at x is minus 1. Okay? That's the x coordinate. What's the corresponding y value? Well, you determine the y value by putting this back into the original function, right? So that's going to be minus 1 plus 3 plus 5 plus 2. So what's that? 10, take 1, 9. That's positive 9, positive 10, take 1, positive 9. All right. So that's how we determine the point of inflection there for that one. Is the inflection point stationary or non-stationary? Explain your answer. Okay, so we've got two ways of justifying whether it's stationary or non-stationary. The first is to look at the graph. and we can see the slope is not horizontal at that point. Okay? The slope is not horizontal at that point, so that means it's a non-stationary point of inflection. The second method will pop up in a moment when we start looking at an example of non-stationary. Okay, so they're the first two questions. Let's have a look at our example in the textbook then. In the notes book, sorry. So the first question I give you is x to the 4 takes 4x to the 3 plus 5. Okay, that's our function. Okay, the question says, state the nature and coordinates of any points of inflection. All right, the nature and coordinates. So over here, I was a bit sloppy actually. I just said there's a point of inflection. We need to declare the nature. So remember, there's two types. It's either stationary or non-stationary. Over here, we established it's non-stationary. The slope is not 0. Non-stationary point of inflection. All right, so that's more precise now. Okay, here's the function. State the nature and coordinates of any points of inflection, and hence state the intervals where the function is concave up and concave down. Okay, so what we're going to do is we're going to start with the first derivative. All right, we differentiate this. We're going to have 4x to the 3 take 12x squared. And I'm going to get the sign diagram of the first derivative as well. Okay, I'm going to take both. So if we want to find the sign diagram of this, we're going to factorize 4x squared. Okay, and again, this is a cubic. It has a positive a value, so it's going to have this shape. All right, we can determine that from the graph if you're unsure how I'm generating. So we graph it, look at it, see that it follows that format. Okay, so that's the sign diagram of the first derivative, right? I'm going to label it there. And so what we've done sort of in 3b and in 3c is we've said, okay, negative slope, horizontal, negative slope, all right? So we learned yesterday that point there is a stationary point of inflection. That's what we learned yesterday. The first derivative has a sign diagram like this. That's a stationary point of inflection. And then here we have a local min, right? Both of those are what we call stationary points. The slope is horizontal at that point. That's from the first derivative. So we already know we have a point of inflection. Okay, let's find the second derivative so we can examine it further. So I'm not going to differentiate this one, right? Because it's expanding. I'm going to look at this. I can just use simple differentiation. We'll have 12x squared take 12x. Take 24x. Factorize 12x. Quadratic, positive a value, so it's opening upwards. Okay, so let's have a look at what this tells us. All right, the second derivative tells you, the sign diagram of the second derivative tells you, point of inflection occurs at the roots and if the sign changes. So here, all this tells us is we have a point of inflection at 0 and we have a point of inflection at positive 2. It doesn't tell us the nature of those turning points. We can look at the graph to determine it. Or here's the other route. Here's the other route, I should say, rather than the other route. The other method is to look at the sign diagram of the first derivative. Now notice how this root appears on both. Okay, so because this root appears on both, that means non-stationary. Okay, this 0, this root, this solution, happens to be on both sign diagrams, so that means non-stationary point of inflection. Sorry, stationary point of inflection at x is 0.
Stationary if they're the same.
Stationary if they're the same, correct, yep. Stationary if they're the same. Alright. But also we know that's true because of this sign diagram, because of the negative negative. Alright, because of the negative negative. We have negative negative next to each other, that means it has to be stationary. That's from 3C. So there's a couple of things going on here. Stationary point of inflection at 0. However, let's look at this one. 2 does not appear on this sign diagram. So because 2 is not a 0 here, it's not a root here, this is a non-stationary point of inflection. Okay? We know it's a point of inflection because it does change sign, right? So we have stationary point of inflection at x is 0, and then we have non-stationary at x is 2. Alright, so we can determine the y value by putting it into the original function, right? So we have stationary at 5, and if we put 2 in, well, we're going to have 16, take 4 times 8, 32, so minus 32, plus minus 16, plus 5, minus 11, we've got 16, 8, 16 plus 5. Yep, I'm happy with that. Okay, so that's what we've uncovered, right? This is the new part when we've got stationary points of inflection and when we have non-stationary. We're asked to answer one more thing. That's the points of inflection. We're saying, when is it concave up? When is it concave down? Well, we look at the sign diagram of the second derivative. Concave up when it's positive, concave down when it's negative. So that means the original function is concave up when x is less than 0 and greater than 2. Alright, it's positive there and it's positive there. And concave down between those points, between 0 and 2. Alright, so I'm going to sketch that function to show you that all of this is true. So we've got x to the 4, take 4x to the 3, plus 5. And zoom out. I just changed my y value. Let's change y to x from minus 5 to 5. There we go. I might zoom out a little bit more. Alright, that's better. Okay, so let's confirm that this is true. If we start at the far left, you can see it's concave up until we get to the point 0. I'm going to put my mouse there right now. That's a stationary point of inflection. Firstly, you can see the shape changing, concave up, and then it transitions into this concave down, right? Concave up to concave down. So that's the first thing we can see there. And that confirms our observation here. Firstly, negative slope, it's decreasing, goes horizontal, keeps decreasing, okay? Stationary point of inflection. And then we found the coordinates of the other stationary point of inflection was when x is 2, y is minus 11, which is there somewhere. All right, can't get it. Let's just graph this line. X equals 2, there. Okay, that's where it changes shape again. So look, I'll trace my mouse along. Concave down, it's opening downwards. Concave up, it's opening upwards. All right, so this exercise is a pretty big exercise, but it's a good exercise because it's a consolidation of 3D and 3C and what we've learned today, 3D. So today, we're probably really only going to work on question 3 and 4. So question 3 and 4, they're both sort of quite big questions. And then in our first lesson next week, we'll have an opportunity to tackle some of the later parts. So let's have a bit of a go at that. Points of inflection, follow the rules, look at the shape, use your graph to support you.